Hi everyone and welcome to the presentation. The title of our paper is Analysis of Drone Propagation with Ray Tracing from sub 6 GHz frequencies up to terahertz frequencies in a real-world urban environment. And I am myself Mohammed Usman Sheikh, and I am a postdoctoral researcher at AALTO University in the Department of Communications and Networking. The other co-authors of this paper are Carl Lerutik, Norshaida Sabah, Edward Mutafangwa, and Professor Rick Kuyanti and Professor Yuri Hamalainen. Here comes the abstract of the paper. As we all know, this unmanned aerial vehicle communication is getting quite popular, and these UAV platforms has been also considered as an effective solution to provide an extended or homogeneous coverage for the terrestrial users. Therefore, the first target of our paper is to analyze the propagation characteristics of the ground transmission at different frequencies. For example, 3.5 gigahertz frequency, that is one potential band for 5G. Then we have a couple of frequencies from millimeter waves like 28 gigahertz and 60 gigahertz, and other frequencies up to 180 gigahertz with a step size of 20 gigahertz. In our simulation, we also try to analyze the impact of drone heights. That's why we have considered different drone heights from 50 meter up to 250 meter. Actually, in most of the countries, they have a restriction for flying the drones above 250 meter heights. That's why we limited our analysis up to 250 meter drone height. Then we also studied about the validity of a previously proposed geometrical line of sight probability model between the ground UE and the drone. And based on our ray tracing simulation, we propose a new modeling parameters for the line of sight probability model. In the last part of the paper, we compared our ray tracing results with those reference geometrical line of sight probability model and our proposed tuned line of sight probability model. Here we are going to discuss about the analytical model for UAV propagation, and on the slide you can see there is an equation for the line of sight probability for a link between the UAV and the terrestrial UE, and in this equation the terms A and B are the environment dependent parameters, whereas theta is the elevation angle between the ground and the terrestrial UE. And if we know about the line of sight probability, then the non-line of sight probability will be equals to 1 minus the line of sight probability. From the reference protein, we have found that the reference values for the parameters A and B is 9.61 and 0.16, and we are taking this value from reference 14, and we are going to use this value in a reference model. Then the mean path loss in dB scale can be given by the equation written here, and there are two additional terms, which is the additional loss in the line of sight and the additional loss in the non-line of sight. And again, in reference 14, we have found that in the urban case, the additional loss in the line of sight is equals to 1 dB, and the additional loss in the non-line of sight is equals to 20 dB. And we are using these values in our simulations for reference analytical model. Here we are going to discuss about the simulation environment. The first thing I would like to tell you that we have developed our own 3D ray tracing tool in MATLAB at the university, and this tool is a sophisticated 3D ray tracing tool, and it is based on image theory. And we have used this tool for finding the propagation paths between the drone and the ground UAV. On the right hand side, you can see there is a 3D building model, and we have considered this downtown area from the Helsinki city. It is a real world urban environment, and it has building of different heights and different types, and also it has a variable street width. In the down there is a 2D picture of the environment which we have considered. In down picture, you can see there is a blue dot in the middle, and that is the location of the drone. And we have placed the drone at different heights as mentioned in the abstract, and we tried with the drone height starting from 50 meter up to 250 meter, and then the red dots are the position of the receiver points. We have created a regular grid of receiver points, and at each receiver point we have considered that the drone that the user is at the height of 1.5 meter, and we have also considered an omnidirectional antenna at the transmitter end and as well as at the receiver end. And the mutual separation between the ground users is 5 meter, and the maximum transmission power in the downlink direction is set to 30 dBm, which is equals to 1 watt. Here comes the result, and the first result is about the line of sight percentage between the drone and the outdoor UE. And we have acquired these results by using the ray tracing simulation data and real world urban environment from Helsinki city and the user grid, which we have shown earlier. And one can see that the height of the UE has an impact on the line of sight condition and the propagation environment between the terrestrial UE and UAV. And it can be seen from the figure shown here that the LOS percentage increases with the increase in the height of the drone. For example, at the height of 50-meter drone, we have only 14% users in LOS with the drone, and when we increase the height from 50-meter to 75-meter, the percentage of LOS user is increased to 23%, and at the height of 200-meter we have 54% users ground UEs in line of sight with the drone. Actually, several countries have restriction on flying the drone above 250-meter height. That's why we have limited our analysis only up to drone height of 250-meter in our rest of the results. Here in this slide, you can see the CDF of received power, which we have acquired through ray tracing simulation data at 3.5 gigahertz frequency only, and for different heights of drone, that is for 50-meter, 100-meter, 150-meter, and up to 250-meter. One thing you can see that for the low flying drone at 50-meter height, there were 2% of the users which were in complete outage, as our ray tracing simulation tool was not able to find any propagation path between the drone and the UAV for a given number of reflections and diffractions. But as soon as the height of the drone is increased from 150-meter to 100-meter, it was able to find the propagation path, and therefore there was no user in outage. And the trends of the graph can be seen here. As soon as the height of the drone is increased, the CDF starts to shift in the left direction. One thing it can be seen here that at 3.5 gigahertz, the receive power levels with the UAV are still acceptable. For example, they are much better than minus 120 dBm, and normally minus 120 dBm is set as a threshold for defining outage. But these results are only for 3.5 gigahertz frequency. At the higher frequencies, we are expecting these graphs, these CDF graphs, to move in the left direction, and at higher frequencies there can be outage. This slide presents a result about the mean received power level, and there in the figure you can see it's a three-dimensional figure. On the x-axis we have frequencies in gigahertz, in the y-axis we have the drone height in meters, and in the z-axis we have the mean received power level in dBm. One can see from this figure that when we increase the height of the drone from the 50-meter to 75-meter, although the distance between the drone and the UE has increased, but at the same time the line of sight percentage is increased, and also the coverage of the cell is improved, and that's why we can see that the mean received power has improved while the drone changes its height from 50-meter to 75-meter. But then after that, from 75-meter onward, again the mean received power level is reducing. And then for a given scenario, and we can see from the ray tracing simulation data that for the given environment and the user grid, the 75-meter down height is found as an optimal height in terms of received power levels. Another thing which we can notice from this figure is that the mean received power level drops by almost 20.5 dB and 33.5 dB while migrating from 3.5 gigahertz frequency to 28 gigahertz and 60 gigahertz. So there is a sharp change in the received power level when we are migrating from 3.5 gigahertz frequencies to 28 gigahertz and 60 gigahertz. And another important thing which we can see here, that we have significantly high atmospheric absorption loss at 60 gigahertz, and that's why as compared to 80 gigahertz, and that's why the mean received power level is at 60 gigahertz is less as compared to the 80 gigahertz. But after 80 gigahertz, again the atmospheric absorption loss is not that much high, and that's why there is a linear decrease in the received power levels. And yes, Overall, for other frequencies and for other down hearts, you can see the mean received power levels from the ray tracing simulation data. Here you can see the line of sight probability results. There are 9 figures, and those 9 figures are for different heights of the drone. In each figure you can see there is a simulation data, and we have used the ray tracing simulation data for finding the line of sight probability. In the x-axis you can see there is an elevation angle, and in the y-axis there is a line of sight probability. And then we have a reference model as discussed earlier. In the reference model we are using this geometrical line of sight probability model, and for the parameters A and B the values were 9.61 and 0.16. Then there is a red line which is the tune model. In the tune model we are using exactly the same probability model, but we use curve fitting for finding in the right values of A and B for the line of sight probability model, and that's why we are calling that one as a tune model, and we use curve fitting on the ray tracing data. It can be seen from the figures that this reference model is very much optimistic, and that's why it is showing a very good line of sight probability at different heights of the drone, whereas in real the tune model the line of sight probability is not that much optimistic. And in another figure you can see the values of A and B which we have found by using the curve fitting on the ray tracing simulation data. It can be seen that when the drone was flying at the low height we have a very wide spread of samples in elevation angle, but as soon as we are increasing the height of the drone, the spread of elevation angle starts to get shrink, and that's why if you're comparing the results of 50 meter and 250 meter, you can see there is a wide spread of elevation angle in 50 meter drone height, and there is less spread of elevation angle with 250 meter UAV height. Here you can see the CDF of line of sight probability which we have acquired by using a user grid which we have shown earlier in simulation environment for reference line of sight probability model and tuned line of sight probability model. Before discussing the results, I think it is really critical to highlight here that the parameters of reference line of sight probability model given in the paper 11 at reference 11 was for low altitude platforms, which means that those they have considered drone at the height of few thousand meters, whereas in our paper we have only considered low flying drones, which is in which we have limited the drone height from 50 meter up to 250 meter. And this is also one reason that we can see in the reference line of sight probability model the results for the line of sight probability is very much optimistic, whereas in the tuned line of sight probability model they are giving the realistic values of line of sight probability for different heights of the drone. If you look at the 10 percentile values of line of sight probability for the reference model, they are 0.82, 0.94 and 0.98, which means that almost more than 80% and 90% of the users are having a line of sight probability, whereas when we look at these 10 percentile values of our tuned model, then it is 0.23, 0.33 and 0.44 at 150 meter, 200 meter and 250 meter respectively. And another thing which we can see that the behavior of reference model becomes almost identical for the drone height above 175 meter, whereas our tune model there is a clear distinction between the line of sight probability for the drone heights even above 175 meter. Here in this slide, in the upper right corner, you can see results about the root mean square error between the reference line of sight probability model and the ray tracing data. And in the lower right corner, there is a root mean square error between the tuned line of sight probability model and ray tracing data. If you remember that we had this parameter, this additional non-line of sight loss parameter. So we have used 4 different values of this additional non-line of sight parameter to find the minimum root mean square error for the reference line of sight probability model and our tuned line of sight probability model. And on the left figures you can see
for reference line of sight probability model, mainly it is dominated by the additional non-line of sight parameter equals to 20 dB. Whereas for the tuned line of sight probability model, there is a clear pattern. For example, for frequencies less than 60 gigahertz, the additional non-line of sight parameter should be 5, and for 60 gigahertz it is 15, and for other higher frequencies it should be a 10 dB. One thing, it can be seen that the tuned line of sight probability model is giving a very low value of root mean square error at all frequencies and heights, whereas the reference line of sight probability model has a quite high value of root mean square error with ray tracing data. Here comes the conclusion. Actually, in this paper, we studied about the radial propagation characteristics of the UAV at different heights and frequencies in a real-world urban environment. The obtained simulation results shows that the percentage of users in LOS increases with the UAV height, and the quiet ray tracing simulation data shows that at 50-meter height, the LOS percentage was 14%, and it was increased to 68% by increasing the UAV height up to 350 meter. The ray tracing simulation data also indicates that the line of sight probability function and the parameters given in reference 14 gives highly optimistic values for the line of sight probability, whereas for our proposed new set of parameters which are acquired by using curve fitting based on ray tracing simulation data gives quite accurate and realistic values for the line of sight probability. Finally, our recommended values of additional non-line of sight parameter in the analytical path loss model reduces the root mean square error between the ray tracing simulation data and the analytical results. So if you have any question, please feel free to ask me. Thanks.